Here is the next example. Here we are finding the resonant frequency for the given circuit. So step 1, we need to convert the given circuit into frequency domain. So this is going to be J2 omega. This will not change, that's 2 ohms. This is 1 over J omega C. C value is 1, so it's 1 over J omega. Now, one of the student had a great idea. Okay, professor, what I'm going to do, I'm going to convert this by using source transformation theorem, okay, or source transformation principle. So I have a voltage source in series with a capacitive reactance. For sure, I can convert this into a current source in parallel with the capacitive reactance. Okay, so I'm going to do this. Now, here is my circuit. It's just like RLC parallel circuit. When it comes to the RLC parallel circuit, we know that omega naught equal to 1 over square root of LC, or F naught equal to 1 over 2 pi square root of LC. So I can convert this and use this formula. No, you cannot do that, because the characteristics of this circuit is different than characteristics of this circuit. So the resonant frequency for this circuit and this circuit, they're not going to be same. They're not going to be same at any time. So never ever do that to find the resonant frequency. So this is a wrong method. Okay, never ever transfer the circuit into some other elements or some other circuit. Okay, so for the given circuit, what I'm going to do, I'm going to find the total impedance. Always, to find the resonant frequency, all you need to do is find the total impedance and then make the imaginary part equal to 0. So I can clearly see these two are in parallel. So 2 parallel with J2 omega, and this combination is in series with 1 over J omega. Okay, this look like a very simple equation, a very simple circuit. You need to have a little bit patience to solve this mathematical equation. So my Z total equal to, I have 2 parallel with J2 omega, which is in series with 1 over J omega. Okay, so what I'm going to do, I'm going to find this value. So the parallel combination, which is 2 times J2 omega over 2 plus J2 omega. Okay, for time, I'm going to take this as Zx. For time, I'm going to keep that separate. So Zx is that. So which is J4 omega over 2 plus J2 omega. I can take out 2, so it's going to be J omega over 1 plus J omega. Okay, my apology, it's a J2 omega because it's 4, right? Now Zx equal to J2 omega over 1 plus J omega. Now my Z total equal to Zx plus 1 over J omega. So J2 omega over 1 plus J omega plus 1 over J omega. Now what is the imaginary term in this? Now remember, it is impossible to separate the imaginary part if you have imaginary term in the denominator. So what we need to do is eliminate that imaginary term in the denominator. So what I'm going to do, I'm going to take the Zx and eliminate the imaginary term in the denominator. So J2 omega over 1 plus J omega. So to eliminate the denominator, J term in the denominator, I'm going to multiply this with complex conjugate of the denominator. Okay, so complex conjugate is nothing but if you have Z equal to 3 plus J4, that complex conjugate we indicate with the Z star. Okay, we call this as conjugate, Z conjugate. Z conjugate equal to 3 minus J4. Okay, if you have Z equal to minus 3 minus J4, Z conjugate is still, it's minus 3 plus J4. Only imaginary part is going to be changed. The sign of the imaginary part is going to be changed, not the real part. Okay, now when I multiply this, it's going to be J2 omega minus j square 2 omega square, and in the denominator it's a plus b times a minus b, so a square minus b square, so 1 square minus j square omega square. J square is nothing but -1, so this value is going to be 2 omega square. I'm moving this part to the front side, so j square is nothing but -1, negative, negative, positive, so 2 omega square plus j2 omega over 1 plus omega square. This is the imaginary, that's the zx. Now my z total equal to, I'm going to separate the real part and imaginary part, 2 omega square over 1 plus omega square plus j 2 omega over 1 plus omega square, and I have minus j over omega. I told you do not separate j and omega, but here it is okay, so that I can see imaginary part and make it equal to 0. So what is the imaginary part here? This is the imaginary part, and make it equal to 0. So when I make that imaginary part equal to 0, so to make the imaginary part equal to 0, to find the resonant frequency, so I made the resonant part equal to 0. Okay, so I have 2 omega over 1 plus omega square equal to 1 over omega. If I move the omega to the other side, 2 omega square equal to 1 plus omega square. Okay, if I pull everything to the other side, 2 omega square minus omega square equal to 1. Okay, 2 omega square minus omega square, which is omega square, equal to 1. So omega equal to square root of 1 plus or minus 1. I'll take that as a plus 1, because omega will not be a negative number. Okay, so 1 radian per second. Okay, so, and f naught equal to 1 over 2 pi, basically free hertz. This is the resonant frequency for this given circuit. So as I mentioned, important point, never ever transfer the circuit to make it simple, and never ever use this formula to find the resonant frequency. Say if I use this formula, what is the resonant frequency here, which is 1 over square root of 2 times 1, so it is 1 over square root 2. Do we have that number? No, I found omega equal to 1 radian per second. Okay, so never ever transfer the circuit first thing, and do not use f naught equal to 1 over 2 pi LC as a resonant frequency formula if it is not RLC series circuit or parallel circuit. So every circuit will have its own resonant frequency. Okay, we need to find that by finding the total impedance of the circuit and making the imaginary part equal to 0. I'm going to make another video by solving another example. Thank you.